Hello, everybody. It is time to start our discussion on how stars will die. So, we've talked about that stars are born. We've gone through the formation from a molecular cloud to a main sequence star. And the next topic in this class is how stars will eventually, after their main sequence life, leave the main sequence and go on their various paths, dependent upon their mass, towards their ultimate deaths. Low mass stars will ultimately die in a planetary nebula, and high mass stars will die in some of the most energetic events in all of the universe, supernovae explosions. So what you can see here on this slide is a astronomical object called a planetary nebula. It is the death throes of a low mass star. This is what will happen to our sun in roughly 5 billion years. However, our sun right now is happily living the prime of its life on the main sequence. So before we can actually get to the death cycle of stars, to understand how the stars will eventually die and then send most of the material back into the interstellar medium, we first have to understand how stars live their life on the main sequence. Over the 10 billion years or so that a sun-like star, a one solar mass star, will be on the main sequence, not really moving anywhere on the HR diagram, there are subtle changes happening. And these subtle changes are the precursors, and they really tell us the physical mechanisms that'll help us understand the death cycle of stars. So let's go ahead and take a look at main sequence life. Let's assume that we have just finished forming a sun-like star. So we went through the Titari phase of a one solar mass star, all the way through to its final adjustments where hydrogen fusion kicks on, and then it ends up on the main sequence. And as soon as it ends up on the main sequence, we say that it has zero age. So right whenever the star is first born, our sun, and we can use the sun as our example, would have basically a core that is an even mixture of hydrogen and helium. That would be true for the entire star. Remember, the core is where the fusion reactions are happening. So we want to actually see how things will change as fusion proceeds. So let's look at the core. And right at birth, it's an equal mix of hydrogen and helium, about 91% hydrogen, 9% helium. But the core is where the proton-proton chain is happening, and hydrogen is being fused into helium, generating energy, powering the star, giving it its luminosity. But notice that the hydrogen is being converted into helium. It's being fused into helium, which means that over time, helium will start building up in our core. And really, this is especially the case since there are no mechanisms. The core and the surrounding region, energy is only transported by radiation, electromagnetic radiation. There's no convection to physically move the stuff around. So we're going to be slowly building up helium in our core. And another key point that we need to keep in mind, because this is like one level deeper, but it's really important to picture in your brain. So here I have the core of the sun, or the core of a zero age sun-like star. It's an equal mix of hydrogen and helium, but the central regions are going to be the densest and the hottest. That's where gravity is squeezing everything together the tightest. So right at the very center of the star, the temperatures will be the highest. And then as you move outward, you'll go from the 15 million Kelvin core temperature to 14 million Kelvin to 13 to 12, and all the way at the boundary of the core at about 10 million Kelvin, because if you're cooler than that, you can't support the proton-proton chain. So it's hottest in the central regions, and where it's hotter, hotter is going to translate to fusion reactions proceed faster. So it's more vigorously converting hydrogen into helium in the central regions where it's hotter than in the outer regions of the core where it's a little bit cooler. So whenever we start building up helium in our core, it's going to build up in the central parts more than it'll build up in the outer parts of the core. Which means that after, say, 5 billion years or so, which brings us to the midpoint of the main sequence lifetime of a sun-like star. 10 billion years is the total main sequence lifetime. This is the current age of the sun, so this is about where we are with our sun. So fusion has been going on for 5 billion years, slowly converting hydrogen into helium in the core, doing it more efficiently in the central regions than the outer regions. So in the core, we are having a higher concentration, relatively higher amount of helium due to hydrogen. In other words, the core of the sun is becoming helium enriched, bringing the fraction of helium from the 9 to 10% to 20% to 30% to 40% helium. So it is just increasing in the amount of helium. And we're going to be preferentially building up this helium in the central region since that's where we're having most of the hydrogen fused into helium. And then another 5 billion years from now, eventually that central region of the core of the sun will have taken all the available hydrogen there and converted it, fused it into helium. So our very central part of our sun-like star has become a one has become 100% helium, but the temperatures are not high enough to fuse hydrogen or to fuse helium into heavier elements, carbon and oxygen. So that means at the very central core of our sun, after 10 billion years, we have built up helium to a 100% level, and the temperatures are insufficient to fuse helium, so there's not going to be any fusion happening in the very central regions of the core. Sure, the outer edges where there's still some hydrogen hanging around have fusion going on, but the very central part of the core of the sun at that point will no longer have fusion occurring in it. And it's at that point where we lose the very central part or the central core region fusing anything. It's not producing energy. That's going to mark the death or the start of the death cycle of our star. It'll end the main sequence life. Because if it has no fusion occurring in that very centralmost region of the core, then it's not going to be producing a whole bunch of energy. The outward pressure is going to plummet, which means that gravity can now take the higher density helium core and start collapsing it, pulling it together ever tighter and tighter and tighter. So we'll stop fusion in the central regions of the core, and gravity is going to start pulling the core together. Hydrostatic equilibrium is broken in the core of the sun after 10 billion years. So what kind of changes does this take? And notice here, here we mapped what the core looks like, and here we're mapping out the entire distribution of helium to hydrogen in the sun. And this is for 0 age, this is for midlife for a sun-like star at 5 billion years, and this is for 10 billion years. And I have the pictures corresponding to the previous slide. They're evenly mixed, so this is the percent mixture, and then this is distance from the center. So this would be the very center of the sun. This would be the surface of the sun, the photosphere of the sun. And after about 5 billion years, you start increasing the amount of helium in the core compared to hydrogen. There's not 100% helium in the central regions of the core, but it's mostly helium now. And as you go to the edge of the core, you still have plenty of hydrogen to fuse into helium. And you don't really get much mixing going on in the outer layers. The fraction of hydrogen to helium remains about the same. And at the end, you have built up the very central region is now 100% helium, 0% hydrogen. And then you have a smooth transition from 100% helium, so you're starting to get some hydrogen to more and more hydrogen. And then the outer layers are still about that 90% to 20 or 10% hydrogen to helium ratio. And what I want to do here is I want to see what kind of changes we're talking about. Previously, we only talked about the core changes. But as the core becomes denser, as it becomes enriched in helium, a denser element than hydrogen, then gravity is going to cause it to contract. So it's going to become smaller. And if it's becoming smaller, it's going to start increasing in temperature, which means that everything around it is going to increase in temperature as well. So as the hydrogen fuses into helium, the core will slowly increase in the relative amount of helium in its core, and it's going to become denser and start contracting. And as gravity contracts it, the temperature is going to go up, and the temperature going up in the core regions means that the fusion reactions are going to go up. the reaction rates are going to go up. You're going to be more vigorously converting hydrogen to helium, producing more energy in the core of the sun. And that means that you're going to increase the luminosity. So as the sun ages from its birth at zero age all the way to the end of its main sequence life, 10 billion years later, the luminosity slowly creeps up. It slowly increases as the star ages. So currently, after 5 billion years, the sun is about 30% more luminous. So its luminosity has increased by about 30% from when it first fell onto the main sequence. So from birth to now has been about a 30% increase. And about 1 to 1.5 billion years, there'll be another 10% increase. And I want to be really clear about this one because this is operating on billion-year timescales. And we're talking about very small changes in the overall luminosity of the sun. This cannot be used as an argument to say that this is causing climate change. That is not how this works. You can go ahead and do all the calculations out if you want to. I have them somewhere. I can dig them up if you're really curious. The amount of changes that are happening over human timescales are pretty much not measurable. So no, this is not the cause of climate change. However, over the course of a billion years, the change is significant. So in about 1.5 billion years, the sun will be 10% more luminous than it is now, which means that the temperature on Earth will be higher because we're receiving more sunlight. And this is a really, really, really interesting, although difficult to think about time. Because we always think about that the end of life on Earth will be when the sun dies and becomes a red giant, which you've probably heard before. The sun will become a red giant, and that's whenever that'll be in 5 billion years, and that'll mark the end of life on Earth. Well, we don't have that long. Because after 1.5 billion years, when the sun is about 10% brighter, the temperatures on Earth will be warm enough to have the oceans start to significantly evaporate, which will put a lot of water into the atmosphere. And then we have a lot of water in the atmosphere, which is a very efficient greenhouse gas. So our temperatures will rise due to the greenhouse effect, which will then cause more oceans to evaporate. And as the oceans evaporate, all the carbon dioxide that's locked into the oceans will also enter the atmosphere, causing the situation to just be worse. So temperatures will go up, and eventually all the oceans will go away. All the CO2 that's been locked into the oceans and in the surface of the surface rocks of the Earth will be put back into our atmosphere. Our atmosphere will be about 80 times more massive. Surface pressures would be high enough to squish us flat like a pancake if the temperatures of about 800 degrees Fahrenheit that the Earth would then be wouldn't be enough to kill us. So we would have an unbreathable atmosphere that's almost entirely CO2, that's super thick, that would be massive enough to create surface pressure that would squish us flat, would have no oceans, and it'd be so hot that we couldn't survive. That is called the runaway greenhouse effect. It is what happened to Venus about 4-ish billion years ago, 3.5 billion years ago, and it is coming to Earth in about 1.5 billion years. Yay, happy week 12, everybody. Okay, that aside, I want to go ahead and really clearly state that it is the development of this helium in the core of the sun that we can't fuse into heavier elements that marks the end of main sequence life. So at this point, I've tried to actually give you a visualization of the entire star. So here we have the core of the star that's going to be 100% helium. Then we're going to have hydrogen mixed with helium around it. And then outside of the core, we have just the envelope of the star, as we call it, which is about 90% hydrogen, 10% helium. Not much really going on there because there's no fusion going on there. But at the very end of the main sequence life, after 10 billion years of happily fusing hydrogen and helium in its core, something fundamental will change about the core of the sun. We'll have the centralmost regions being an inert ball of helium. The temperatures are not high enough to fuse it into heavier elements, carbon and oxygen. So whenever we have temperatures that are not high enough to go on to the next level of fusion, fusing helium into carbon and oxygen, then we refer to that as helium ash, or really fusion ash. The helium was produced by hydrogen to helium fusion, but we can't fuse it to anything heavier, so we call it ash. Just like you can't burn ash, it's already been burnt. So we call this core of 100% helium a helium-ash core. And the ash part tells us that the temperatures are insufficient to fuse helium into anything else. However, outside of our helium ash core, we still have temperatures that are sufficient to fuse hydrogen into helium, and we still have hydrogen. So now we have a helium ash core surrounded by a spherical shell of hydrogen fusing into helium, what we call a hydrogen burning shell. And it's when the first moment that the sun develops this helium ash core, that is the end of main sequence life. Because without any fusion in the central regions to fight off gravity trying to pull everything together, gravity will start to win. Hydrostatic equilibrium in the star is broken, and that core will start to collapse. And as it collapses, it'll get denser and hotter. And this will create and start the fundamental changes that we'll track through the core of the star, and we'll look at how the envelope, the non-fusing envelope, responds to these changes that are happening in the core of the star as we go through all the fusion cycles as we can, sort of the last gasps of energy production for a star until the star dies. Okay, so we need to talk about stars of different mass. I think that point has become clear in this class. And one of the things we haven't talked about yet is fusion in the cores of stars that are more massive than the sun. And I haven't really waited until now to introduce this to avoid throwing too many complications on. So it's not a huge process in the sun. This does occur in the sun, but it's a minor player. But there is another fusion reaction of hydrogen into helium that occurs in stars. And it primarily occurs in stars that have masses greater than 1.3 solar masses, 30% more massive than the sun. And in this case, the primary energy production is not the proton-proton chain. It's this set of fusion reactions called the CNO cycle, the carbon, nitrogen, oxygen cycle, where it's going to use carbon, nitrogen, and oxygen atoms that are in the star as catalysts to produce and facilitate hydrogen into helium fusion. So what's shown right here is the core temperature, the central core temperature, and then the relative amount of energy produced from the proton-proton chain versus the CNO cycle. So here, the sun, most of the nuclear reactions in the sun, the energy produced by the sun, is from the proton-proton chain. Something like I think it's about 90% of the energy production. However, at about 1.3 times the mass of the sun, the core temperatures are about 18 million Kelvin. Now, if you go to higher mass than that, higher core temperatures than that, then the CNO cycle produces the majority of the energy of the star. It is the dominant fusion reaction. By no means do you have to memorize the CNO cycle. I only want you to be aware that in stars that are 1.3 times the mass of the sun or greater, it is the dominant energy production during the main sequence life of those stars. Because as you can see, it is a complicated reaction, and it's a catalytic reaction, as in that the carbon, nitrogen, oxygen are the same amount that you start with is the same amount that you end with. They're just there to facilitate the fusion of hydrogen into helium. So you get a net reaction that looks kind of crazy, where you're taking 4 hydrogen and you're creating helium. But notice you have all these other things that are going on because there are several different steps along the way where the carbon, nitrogen, and oxygen and their isotopes are catalyzing this reaction. Oh, and here I did have the numbers, so I was a little bit off. So for a 1 solar mass star, 98.3% of the sun's energy is produced by the proton-proton chain, and only 1.7%. This is why I haven't mentioned it up until now, but it's whenever you get to 1.3 solar masses that it's about a 50-50 ratio. So I want you to be aware of the CNO cycle. I don't want you to memorize the reactions, but I do want to show you how it works. And you can pick up this pretty much anywhere because it's just a cycle. So it just keeps going round and round and round. But let's just go ahead and start with the carbon. So we'll start at the 12 o'clock position. So here you have an isotope of carbon, carbon 12, 6 protons, 6 neutrons. We'll fuse a helium onto that carbon to produce an isotope of nitrogen, nitrogen 13. So it's going to have 7 protons, 6 neutrons. That's an unstable, that's a radioactive form of nitrogen. So it'll radioactively decay into carbon 13, a radioactive isotope of carbon. However, if we can then add and fuse on another hydrogen at that point and fuse hydrogen with carbon 13 to get nitrogen 14. So notice that we've used carbon and nitrogen so far. Now we have nitrogen 14. Let's fuse that with another hydrogen atom, a hydrogen nucleus, a proton, and we can get oxygen 15, a radioactive isotope of oxygen, which will rapidly decay into nitrogen 15. And then with this nitrogen 15, we can fuse nitrogen 15 with hydrogen. And what does that produce? Helium 4, 2 protons, 2 neutrons, and carbon 12. And we're back at the start of our cycle. So this can facilitate, and each one of these reactions releases energy, and the net result is you're taking all of these hydrogens and you're making helium. So it is a hydrogen to helium fusion reaction. All right, I know the CNO cycle is pretty complicated. You pretty much just need to know about this slide. It's the key takeaway I want you to have. Thank you for tuning in. I'm going to next talk about the general way that stars evolve off the main sequence, a general pattern that we can follow, because there's a lot of rhyme and reason. And if we can have a strong backbone of understanding a generalized prescription of how things proceed, that should help us get through the complicated changes that are happening in the cores of stars. So we can follow a sun-like star. That's how we'll start from it leaving the main sequence, it developing a helium-ash core, all the way to its death as a planetary nebula and eventually a white dwarf. I will see you in the stellar evolution videos.